Okay, so let's continue where we left it yesterday. So let me recap first. We want to, we were trying to use the S matrix to understand like time evolution, and in particular its classical limit. So we have that the S matrix gives us the scattering amplitude. We were focusing on the scattering amplitude of two massive scalars, say, scattering gravitationally. And I promised you that we would see how this should take this exponential form, where this object I is some classical on-shell action. And this happened in the following limit. So we had this separation of scales, where we had that the largest scale was the separation between the particles. Okay, so this is a regime, long distance, where we think we can actually resum certain things, do perturbation theory. Then there's this characteristic length scale of the gravitational interaction, which will be kind of the effective Schwarzschild radius of each particle, and then the de Broglie wavelength. This was like 1/m, this goes like gm, and this goes like 1/the momentum transfer between kind of the initial and the final state. Okay, so there's this q, which was kind of the difference between P1 and P4. Okay, so we had two small parameters in the problem because we have two hierarchies here. We had q over the mass or q over the momentum. So this is what controlled kind of quantum corrections versus classical corrections. So we were expanding in small p, or sorry, in small q. And also there's GMQ. And this just is essentially like GM over B or GM over R. So this just controls kind of classical weak field corrections. And because we were doing perturbation theory, we were trying to dig these kind of terms from the amplitude. Okay, so we explained these rules for power counting. So essentially every in the relevant region, every graviton momentum, you should think that goes like, its propagator goes like 1/the momentum transfer squared, because the graviton momentum goes like the momentum transfer. If you had a matter propagator, typically it had been kicked by some graviton, so we could expand this away in this limit where the graviton momenta are small. So this went like 1/q times m, right? The leading order was p dot q, so p is of order m. So I had like 1/q dot m. And then the vertices, we were just adding like powers of the mass per vertex, but there could also be subleading corrections to this. Okay, and we did 3 examples of some diagrams which are inside of the scattering amplitude. Okay, notice that all of these diagrams you could construct in principle using this kind of 3 point amplitudes that I explained in the second lecture, like 2 scalars, 1 graviton, or 3 gravitons. And we saw that, okay, this one just goes like 1/q squared, so the Fourier transfer would give us a Newtonian potential or a logarithmic divergence in impact parameter space. But here, we had the triangle diagram, which was suppressed by 1 power of GMQ with respect to this. So this we identified as a classical correction to the scattering, okay, just of this form. This is one of the small parameters, right? But then this bubble diagram was actually 1 order further suppressed. So instead of GMQ, this was GQ squared. So this was actually a quantum correction, okay, because this is Q over M relative to this. Okay, so I told you that this was something like, would encode like a quantum correction to Newton's potential. Okay, but we left out kind of one diagram, which is this box diagram. So first thing I want to do today is I want to go back to this box diagram and explain what was up with it. Okay, so we want to understand this diagram. So we have P1, P2, this is minus P2 minus Q, minus P1 plus Q. So this momentum is going to be L, it's going to be Q minus L. And it turns out that they will be convenient to actually add also the cross version, where I just exchange 2 and 3. Because we'll see that something nice happens. So with the same labels, this is L, this is Q minus L. This is P1, this is P2. Okay, so let's look at what this looks like in the leading order expansion in using this counting. Okay, so this, I will have the usual loop momentum. Yeah, also they mentioned the measure also had some power counting. So DL, this gave me a factor of Q to the D. Okay, and then these two propagators are in common to both diagrams. So let me just write them. Actually, these three propagators, because here I have P1L, so this is going to be minus P1 minus L. Same holds here. Okay, so the following three propagators are in common: L squared, Q minus L, and this one, which I'm going to expand to the leading order. So this will be 2,1 P1 dot L. And then what's the difference between these two? Okay, let me write first the unexpanded version. So this one here, notice that L here is incoming, so this is going to be L minus P2 squared minus M2 squared. And importantly, I'm going to add an I epsilon that I will have to keep track of, which is something that so far I didn't worry too much about. And then there's a contribution from this one, which is the same thing, but instead of L, is Q minus L, which is entering here. Okay, so here I will have Q minus L minus P2 squared minus M2 squared. And now I'm going to expand this. So this one will look very simple in this limit. This will look like minus 2 P2 dot L plus I epsilon at leading order. This one is going to look at 1 over minus 2 P2 Q minus L. Also, I will keep track of the I epsilon. So before I do any calculation, before I proceed further, let's power count, because now I expanded all the propagators, right? So what's the expectation here of each of these diagrams? So each of these diagrams is going to have a Q to the D from the measure. I have 2 graviton propagators. So this will give me 2 powers of this Q squared. Now I'm just using these rules here. I have these vertices here. So I'm going to have M1 squared, M1 to the 4th, M2 to the 4th, and 2 matter propagators, which are going to give me QM1 and QM2. So what does this go like? This goes like M1 cubed, M2 cubed, and then I have Q to the D. No, Q to the D, just by dimensional analysis. All of the components of the loop momenta scale like Q, yeah. Okay, so this is, let me write it as follows: Q to the D minus 4 over Q squared, okay? So D equals 4, this just gives me 1 over Q squared. But that's the same as this. This is not suppressed. It's not suppressed by anything. So it seems that this is as large as the classical term. Okay, so let's keep going and see what happens. Okay, so we need to understand what's special about this diagram. And this I epsilon prescription will be important. Okay, so let's see. This looks almost the same. The only difference is that there's a P dot Q. However, note that 2 P2 dot Q, what is this? So this is very close to the on-shell condition of P3, right? Because P3 just differs by P2 by Q. And so I can write this as P2 plus Q squared minus Q squared minus M2 squared. But then using the on-shell condition of P3, sorry, not P2 minus Q. But the on-shell, this is just P3, so the on-shell condition of P3 tells me that these two terms cancel. So P2.q is actually order q squared. So I can just drop it, because here L is order q, P is order m, and then P2.q is just suppressed. So I can just drop it. So let me just erase it here. And then I will cancel this minus sign. So what do I have? This combination is minus 1 over 2 P2.L minus I epsilon. I just pulled out a minus sign, plus 1 over 2 P2.L plus I epsilon. Does anybody know what that is actually corresponds to? Yeah. So this thing is, by some distributional identity, 2 pi times delta of 2 P2.L. So we see that this propagator, when I combine this, essentially becomes on shell. Okay, so it's cut. Okay, but then here I can play the same game. I can just relabel, just average over 2 labeling. So now I'm going to take this combination that I have. So I have the sum over those 2 diagrams. So let me call this and let me just add this to the same thing, but with L goes to Q. Okay, this is just a relabeling of the loop momenta. I'm integrating over loop momenta, so I'm able to choose any labels I want. So what does this look like now? This will look like 1/2 ddL 1 over L squared and minus Q squared. I had this delta function on the top to P2.L. And then I have 1 over 2 P1.L plus I epsilon plus 1 over 2 P1 Q minus L plus I epsilon. And just doing the same manipulations, I would learn that this thing here is delta of minus 2 P1.L. Okay, so the answer, this looks like 1/2 ddL 2 P1.L 2 P2.L L squared L minus Q squared. So this looks a bit funny. In fact, what is it? It's just a convolution. So this thing is just 1/2 of a convolution of the tree-level diagram. So the tree-level diagram just went as 1 over Q squared times the tree-level diagram again. Okay. Remember that in our Fourier transform, we also had these factors here. So let me go back to the Fourier transform. So our Fourier transform with SB, this was ddq delta 2p1 dot q plus q squared. But this is small, so let me just expand. 2p2 dot q plus q squared. And then e to the I b dot q times the amplitude as a function of s and q squared. So this also I will expand away, because q is, we said that it's smaller than p. So you see that this measure here is the same as what we have right here. Okay, so you see that the answer here is just the convolution of 2 copies of the leading answer that we had here. Okay, so what happens then when we do this Fourier transform of the box, right? So if we do the Fourier transform, so ddq of, okay, so we have this factor, minus 2, p1.l, p2.l, e to the I, q dot b, of now this combination so we'll find that this is just 1/2 of the square of the tree answer. Okay? Because a convolution, if you do the Fourier transform, just becomes a product. Okay? So this becomes a product because it's the Fourier transform of a convolution. So there's this basic property of Fourier transforms, which is that, yeah, in momentum space is a convolution. So in position space now, because in impact parameter space, it becomes a regular product. Yes? Yeah. So the second delta just came from, I had to do some manipulation, which is that these two propagators I had turned into a delta, but then I still had this propagator here. And just by relabeling two different ways the integral, so I just summed the integral labeled in two different ways. Then I saw that, again, the same combination appears. No, this is the full integral. Then I'm just manipulating this by adding it, and then I have 1/2, so that I don't overcount, of the integral, plus the integral, but choosing different labels for the loop momenta. So this is just adding 1/2 of 1 plus 1. Yes, that's right. It's the sum of the two diagrams, yes. I just put it in by hand. Yeah, I added 1/2 of the sum over the two diagrams plus the sum over the two diagrams, but choosing different labels for my integration. I just did a change of variables. Okay, I could have done it from the beginning and add the 4 labelings, but then the combinatorics here is, is worse. That's why I did it in 2 steps. Yeah. From yeah, from here. Yes. Yes. This. Yeah. Note that these two propagators are invariant, right? And I told you that every time I have a p dot q, I can drop it because this is order q squared. So this one effectively is invariant. Now these two are not invariant because of the sign. And instead, when I add them up, they give me an extra delta function. This combination here gave me another 2 pi delta to p1.l. Yes. Yeah.
Okay, thank you. The 1/2 times of the convolution, it's an exact result in the sense, because there you did some kind of approximation, because of the regime that you're considering, right?
Here also. Here,
this
is, I expanded, for instance, here I was expanding these propagators in this self-limit. So I was using these power counting rules to really expand the propagator to the leading order, and I'm always dropping these corrections.
Okay,
yeah.
Okay, thank you.
Okay, more questions. This is going to be the most technical part of the lecture, so feel free to ask until. So if you wish, this is just the result of a calculation. I could have just computed diagrams, but here I'm showing you without doing the integral that this actually becomes a convolution. But in practice, you could have just added these two diagrams, just compute them, expand in small q, add them up, do the Fourier transform, and you would find this answer. You would find that you just get 1/2 of the square of the tree level answer. And this keeps going, actually. If now I take, if I went to the next loop order, where I would have this plus a bunch of permutations, if I did the calculation, I would find that this is actually 1/3 factorial of the triple convolution of the tree. So when I would do the Fourier transform, I would find that this is 1/3 factorial times the cube of the tree. There's no symmetry. It's just the result of a calculation, if you wish. There's no need for, I mean, the symmetry, if you wish, is that you can permute legs to show it explicitly, like I did there. What I did is I can just permute these legs, and this is some invariant expression. But that's what you're asking. Of course, the point of this is to justify what I told you, which is that actually in this classical limit, the scattering amplitude exponentiates. Yes. Yes. Yes, exactly. Yeah. So let me just write that as an equation. So the statement is that 1 plus I times the amplitude, if I look at the leading term in this series of diagrams, I could keep going. I would need to go to all loop orders, but then if I expand these diagrams at leading order, then I would find that this rearranges in position space, so after the Fourier transform, as just the exponential I times the Fourier transform of the tree.
So, Julio?
Yes.
Here. The intuition is that in this regime, all the massive legs are always on shell.
Yes, exactly.
Is there something else that's happening, or?
No, this is it. It's just the same scattering process of physical particles again and again and again that you're seeing, and it's just encoding this classical process of like a single exchange of a classical graviton. So you see you can think of this gravitons as really like particles, and you need to add an infinite number of them to really see kind of the classical exchange of kind of one classical graviton. Yes, but here we are not going to put it in a cross section. Yeah. No.
Yeah. Like in practice, you only need to know that the Fourier transform is the exponential to get cross sections. I mean. Yes. So this result is really nice. Yeah.
It is really nice. Yes.
One more question.
Yeah.
Why
we will use it. If you just take the absolute value squared of this, you get 1, right? So in a sense, this just tells you that this is just elastic scattering. Right? It tells you that classically you just have these particles bouncing off each other. So the probability of ending with the same particles in the final state is exactly 1, which is what we said yesterday. Remember in this phase diagram of gravitational scattering, we had the Born exchange, which was the leading term of this series. And I told you, you can reach by either increasing the energy or lowering B, you can reach into this kind of classical regime where the cross section or the absolute value of the S matrix is still 1, because the particles don't disappear. I still have elastic scattering, but here it happens in a very natural way, just because the amplitude just becomes a pure phase. And this phase is a classical quantity. So now what I want to explain is, what is this classical quantity?
Okay. Just one more question. Why do you always keep writing M and then regretting it and erasing and writing an A. Is there a reason for choosing A instead of M?
Yeah, some people call the amplitude A, some people call it M, so sometimes I get confused.
So it's the same.
I'm using consistently A in these lectures, that's why. Sometimes kind of my habit betrays me, but
But it's the same.
it's the same thing,
Okay.
yeah. More questions? Yes. I can, yeah.
Well, in general, the process is like all these diagrams plus the bubbles inside, I suppose, right? The bubbles of gravitons and all of that.
Okay, no, so now you will see what happens. Remember, I told you that the bubble was quantum,
Yeah.
right? So actually, the bubble won't exponentiate because it's something quantum. Yeah.
Okay.
So this was always up to kind of 1/order h bar corrections, right? When we do the semi-classical approximation, I'll mention this in a second. So the bubble is there. So
Okay,
the bubble
good,
actually
good,
won't exponentiate.
Okay. Thank you.
My question is closely related to this. Suppose that you do all, for a given loop, for example, 2 loop, or the first example, 1 loop, and you write down all diagrams at 1 loop, or many more than that, and you do an h bar power counting.
Mm-hmm.
So those will be the leading ones, the leading terms.
Yes.
But do you need in this analysis of h power counting to take into account the regime that you're working in or not?
Yeah, that was the separation of scale. So I set h bar to 1. I'm effectively counting h bars by counting powers of q, or q over m. But if you wish, you would see that e square, right? If I restore the h bars in this exponent, there will be 1/h bar.
Mm-hmm.
And that means that the contribution from these diagrams, actually it's singular as h bar goes to 0. It goes like 1/h bar squared,
Yes.
which is telling you that they're becoming very large in the classical limit, which is what we said a couple lectures ago, that g times e squared is large. So there's a 1/h bar there. So there's a classical phase which is very large. That's why we need to resum.
And the remaining 2 one loop diagrams go lower than this. I
Mhm.
mean,
Yeah, so for instance, the triangle has a single h bar, right? So the leading correction to this is still classical, right? So let me write it here. The leading correction will be the triangle. So this is a classical correction, which actually one could also prove that exponentiates, but then I would need to add also diagrams. I could need to add the triangle here. Let me add them on the next board. Right, so now I also want to include the next classical correction. So I will have this triangle, but then at the next order, I will have things like this. And then I will have 2 copies of this triangle and the cross version. And when I add all of those, for instance, this one will be the convolution of the tree-level answer with the triangle. If I do the same manipulations, I will find that these propagators get also on shell, and I will find that it just comes from expanding the exponential. Okay, so all of these corrections that go like GMQ, like the triangle at high orders, we will always find that they exponentiate because they correspond to classical corrections.
Julio, in those other corrections, shouldn't we have some super classical terms as well?
No, the super classical terms are these terms which are too singular in 1/h bar, which are precisely this.
Okay.
So this is what we get rid of by exponentiating. We realize that those terms that are kind of like classical things are things that have like a single 1/h bar.
Yeah.
So this was 1/h bar squared. So this is more classical than classical, but we identified that it's just that I haven't taken the logarithm.
Okay.
Yeah. Okay, more questions? Okay? So if not, let me just explain what is this phase, right? We're computing the scattering amplitude, but what do we expect that this phase corresponds to? Okay. So first of all, we could have computed directly the phase instead of going through this, because remember that there was an alternative way of writing the amplitude as I over n as an operator. Okay? So this is 1 plus IT. So I could have inverted this relation. If I really want to compute directly n, or its matrix elements, I could have inverted this relation and say, let me compute the expectation value from P1, P2, and P3, P4. And this will be something funny because it will be the expectation value of log, or I times this, of log of 1 plus IT, P2, P3. But in perturbation theory, I can just expand the log because this T is always small. Okay, so what does this look like? If I just use the usual formula for log, like 1 plus x equals x squared over 2 dot dot dot, then I'll find that this is just a bunch of powers of x. Okay, so I'll find that this object, let me call it delta, will be something like the amplitude, because the leading term will just be IT. So the leading term will be I times the amplitude. But then there will be something that looks like minus 1/2 P1, P2, IT squared, P3, P4. Oops. So this object is just the usual scattering amplitude. What is this? I can just insert a complete set of states, and this is going to look like this. It will look like a process where I have the two particles scattering once and then again, et cetera, et cetera. Okay? And this keeps going. So we see that the classical piece, I always need to subtract all these kind of rescatterings, and that precisely will compute directly this exponent. That is the classical part that I'm after. Okay. So that's a kind of an alternative perspective, just as an operator of the same calculation that we just did. Okay? And at the end of the day, we're just doing the semi-classical approximation. Okay? So what is I? So if at the end of the day, this S is just the time evolution operator, then typically when we think about the semi-classical approximation, we think of what? We think of particles that have initial coordinates and final coordinates, and we just compute what is the probability, right? So we have schematically something like Q initial, Q final, right? And this is given by some path integral. So let me do it in the Hamiltonian language. Oops. Of e to the I, some classical action, where this is just the usual thing. This is kind of Q dot P minus H, where H is the Hamiltonian. With QI, Q equals QI, and Q equals QF as boundary condition. So this is this classical action. This is not exactly what we're computing, because we're computing a scattering amplitude where we fixed initial and final momenta. Okay? So the actual object that this corresponds to, this phase here, is the following. Okay, so you learned it in Alejandra's lectures. So if instead of fixing coordinates, I want to fix momenta, what should I add to my action? Some boundary term, right? So the actual classical action that I want will be this one, S classical. But then I will add the following. PQ minus ET evaluated the initial and the final time, which then I will send to infinity. Okay, so this is and then my amplitude, which is basically P1, P2, the time evolution, P3, P4, will just be, by the usual semi-classical approximation, just I so this classical action evaluated on the classical trajectories, and then there will be some quantum corrections. Okay, so at the end of the day, when we're taking this classical limit, we're just seeing like this exponentiation. It's just the usual semi-classical approximation. So it's not mysterious. Okay, it's something that we know very well. Okay, and this is also nice because this object, we know that it's also the generating function for various observables, right? Just like in ADS-CFT, right? You take your on-shell action, which is a function of the boundary conditions, and then you take variations with respect to those boundary conditions to calculate various observables. The same is true here. So various derivatives with respect to coordinates and momenta of this thing will give you observables. Okay, and tomorrow we'll look more into that, how precisely we get observables for this. There's a question.
Yeah. So can you repeat again? Why did you subtract like the PQ minus ET?
So
Yeah.
it depends what you want to compute. So if you're computing directly in position space, then you can think of it as the usual semi-classical action, right? But the scattering amplitude, we fix the initial energies and momenta of the particles, right? So I will need to subtract appropriate boundary terms, okay? What is the role of these boundary terms? For instance, the role is to make the variational problem well-defined, right? Because, okay, let me just go very quickly over it. So if I take the usual action that I wrote there, and I do the variation of the usual action with respect to P and Q, what am I going to get? I'm going to get dt, the equations of motion of Q, dq, plus the equations of motion of P, dp. But there's somewhere I have to integrate by parts, right? So there's a term that comes from this Q dot P that I need to integrate. Actually, this is the other way around. So these are just Hamilton's equations. So this will be minus P dot minus dH dq, for instance. This one here. Okay, so there's a boundary term which should look like plus delta Q P total derivative. And in amplitude, I fix momenta. So this boundary term would it cancel if I didn't add this. And actually, this term is similar, because if I fix the energy of a process, actually the initial and the final time of the integration, I have to be able to vary. So the role of this is to just also count a boundary term that comes with the variation of the initial and final time.
I have another question.
So you have reconstructed the classical action in that expression looking at a convolution of these diagrams, of these three diagrams, right?
Well, this is I gave you a piece of this classical action.
Yeah, yeah.
Yes.
There is a piece there,
Yeah.
and you reconstruct the classical action.
Yes.
And eventually you make an identification of the usual procedure we do in that expression, in the sum over trajectories and momentum.
Mm-hmm.
But that boundary term that is there is I mean, you're putting that term by hand,
Yes.
given the knowledge of what we know. I
Yes.
mean, we need to subtract these boundary terms. Usually you need to fix some boundary conditions and so on.
Yeah.
But there is no way to see that piece of information in the diagrams, right? In the reconstruction of what you
No,
can.
because there I'm directly computing this matrix element, right? So I'm not doing a path integral. I'm doing a path
Yeah.
integral, but secretly by computing the diagrams, right?
Yeah, sure.
But implicitly, there was a choice right at the beginning when we were computing an amplitude of some boundary conditions,
Yeah.
which
And that
now, in order to
somehow
match, yeah,
those boundary conditions are there in that term.
yeah.
Okay.
One additional question. Semi-classical approximation means one of those regimes, one of the, for example, that quantum versus classical regime?
Here, by
Yes.
here, the semi-classical approximation, I mean, the usual procedure that you do when you do the semi-classical approximation of a path integral, which is you expand around some classical solution, and then the leading contribution corresponds to this classical solution, right? Like I just
in this case, it's Einstein's Hilbert, or what is he?
in any theory.
In your case,
In my case, this is just the dynamics of a pair of particles. I mean, this is a bit schematic, but it's the dynamics of a pair of particles interacting gravitationally.
yes. Okay.
So I would just evaluate this on the classical solution, the actual classical solution to the classical equations of motion, that a pair of particles coupled to Einstein-Hilbert. I could have computed that solution. The amplitude gave me this object directly, the on-shell action. Alternatively, you could have just gone, coupled two world lines to GR, solve the classical equations of motion, plug them into the action from the world lines, which is this thing here, and then you would have gotten the same result. Okay, so, but the amplitude knows about this when you take the classical limit. It's just recomputing this thing.
Thank you.
I mean, you are able to reconstruct the action.
Yes.
I mean, the explicit action we know of a pair of particles with this approach.
Yes.
Okay, that's
Yeah.
cool. And can you reconstruct the one loop or the determinant that usually is really hard in that approach? I mean, you can.
Well, by the way, even this is very hard in this approach. So the state-of-the-art calculations of this quantity that we have,
Yeah.
they're done using these ideas.
Yeah,
so,
sure. But I mean, my point is that,
Yes, if you kept the quantum part,
yeah,
right, which I'm throwing away, this quantum correction to Newton's potential, et cetera, principle that corresponds to this order h bar correction. So I told you that here, this was 1 plus order h bar, where here there was this bubble, for instance. So that encodes these kind of things. But this is all perturbative, so I don't know.
Yeah,
if
sure,
it's,
sure.
yeah.
Another question. Usually in these one loop determinants, there are zero modes in these calculations, and it's really hard to get rid of these zero modes.
This is not the case here. Maybe we can have a discussion about that later.
Okay.
Yeah, because this one loop determinant is not the main point of what I'm trying to say. Yeah. If it's directly related to yeah, okay, yeah. Sounds good.
Sorry,
Okay.
if this, sorry,
Yeah.
if this I somehow related like to a legendary transformation, because the legendary transformation takes
Yes,
velocity
this is
coordinates
effectively
to
like
momentum.
the change in boundary conditions is effectively a Legendre transformation,
Oh,
but only in the asymptotic data.
oh, okay, in the asymptotic data.
Yes.
Okay.
Okay. Good. So this is the end of this discussion of exponentiation. So as I promised, I showed you that the amplitude, so we have these nice principles that constrain it, which, okay, maybe they come from thinking about quantum mechanics, like unitarity, et cetera, but they provide us with a very efficient way to compute some of these quantities. And then if we take the classical limit, we can identify which terms are classical and how they exponentiate. In practice, we never compute this whole series of diagrams. Whenever we have a classical piece, we just know it's going to exponentiate, so we just go to the first order where it appears, and we just compute it once. Okay. So we don't need to do all of this work over and over again every time we get a new piece. Okay, now I want to switch gears a little bit and talk about various expansions. So I want to draw another phase diagram, but now it's purely classically, okay? So we already understood by some separation of scales how the classical process emerges from the quantum amplitude. So it emerges essentially as a logarithm of the amplitude, so as some semi-classical action, right? So now we're going to focus from now on this classical process and also think about which other expansions I could have of this classical thing. Because at the end of the day, some of these diagrams are going to have to compute. They depend on various parameters, and we want to understand also where various pieces of dynamics come from. For instance, we would like to identify where is the metric. Like here, there was no metric anywhere, right? Is the metric hidden somewhere in this calculation, right? Maybe just the long distance metric. Or, okay, where is the Newton's potential or its corrections? Where is gravitational radiation hidden in these calculations? Okay, so this is now the phase diagram of binary dynamics. Okay, so this is purely classical. So again, there will be two axes. There's actually more axes because you can have spin and other degrees of freedom, but I'm just going to focus on the simplest. So the first one is going to be B over GM. Okay, B over GM was just the inverse of one of our perturbative parameters, right? So this is 1 over GMQ. So more classical, weak field is going up, okay? Because this parameter is very small, so this is large in the weak field. And then I'm going to focus also on the mass ratio. So I'm going to have now one particle to be very heavy, and then the other one to be small. Okay, they both move. But here I'm going to have M over M. So how do we compute in this phase diagram? Because in principle, this is a hard problem. In particular, down here, we have strong fields and comparable masses, right? So for instance, the black holes that LIGO has measured are somewhere near here towards the origin when they merge. Okay, and here, the only tool that we have is numerical relativity, which is what I said yesterday. We just actually take Einstein's equation. We don't play this game of amplitudes or anything like that, and we just solve them on a computer. Okay. I told you when the mass ratio goes around 10, or if you have like some large hierarchy of scales, like any numerical method, numerics don't play well with large numbers. But this, if we have a large number, typically we can take its inverse and we have a perturbative parameter. Right? So there's going to be two regimes here. Here there's going to be the weak field. And there's two expansions here, PM and PN, post-Minkowskian and post-Newtonian, which I'll describe in a second. And here we have the so-called self-force expansion. Okay. So what are these expansions? So the post-Minkowskian expansion is just the weak field expansion. It's just the expansion in GM over B, or GM over R, if you wish, where R is the separation between the objects. So this is just saying you have two objects, they're far away from each other, they just feel the weak field of the other object. And there we can do perturbation theory, which is what we've been doing so far. We've precisely been identifying these sort of corrections. Okay. The other more traditional perturbation theory is called post-Newtonian. the impact parameter, right? Like before, the Fourier transform, the Fourier conjugate of Q, of the momentum transfer. Right, remember this picture of the two objects which they're initially separated by some impact parameter B. Okay. Anyway, this is this PM, and this is PN. Okay. So post-Newtonian is also expanding in small velocities, right? Because for a virialized system, we have that the kinetic energy is of the order of the potential energy. So for any bound system, we expect actually that GM over R, and actually now let me put back the factors of C in the Schwarzschild radius. So secretly, there's a C squared in the Schwarzschild radius that we always forget about because we said C equals 1. So this is going to be of the order of V squared over C squared. So this is just the equality of kind of kinetic energy with potential energy, and they're both small. Okay. And this is, for instance, the regime that we have in a binary merger that we observe in gravitational observatories in the so-called in-spiral phase. So when they're very far away from each other and they're slowly moving, getting closer, but very slowly because they're virialized. So if they're far, then they're going to be moving slowly. Okay. So one of the goals will be to understand how to do this velocity expansion. But first, we will do the other one. So there's the self-forced expansion, which is just an expansion in the mass ratio. So if we have an object which is much heavier than the other object, then we know that, for instance, at leading order, so-called probe limit, we could treat one of the objects as fully back-reacted. So we have like some black hole metric, and then maybe there's a smaller object, which is a probe, moving in this kind of black hole space-time. So when we solve geodesics for Schwarzschild, we're always in this probe limit. But of course, this also has corrections, because this is only to leading order in the mass ratio, but there's going to be corrections which go like little m over big M, where little m is the mass of this object, and big M is the mass of the black hole. And this is essentially the back reaction due to the small object. Yes, there's a question. One particle in flat space. One particle in flat space we'll discuss in a second. So what you can see is how you reproduce the metric. But then there is no expansion, because you just have one particle. Yeah. So if you have just one particle, you can go to a frame where it's at rest, and then you just have its field, static field as measured from far away. Yeah. Okay, so in the rest of my time, I want to quickly explain these two regimes. Okay, so how do I identify, for instance, this probe limit inside of the amplitude and its corrections? And how do I identify various velocity corrections inside of the amplitude? So first I'm going to do the mass counting. So first I'm going to focus on this regime. And this will be very easy because we were taking the small q limit, but the other reference that we had was the mass. So secretly, when we were doing small q expansions, we're also doing like large mass expansions. So we just need to look at which diagrams gave us which powers of the mass to identify the various probe type contributions. Okay, so remember, in the power counting rules, we have both factors of q and factors of the mass. So for instance, when we had this action at the leading order, this went like gm1 m2 squared over q squared. So this was at order g. At order g squared, we just computed one triangle diagram. So we had like a gq, and we had like m2, but there's also the other triangle diagram, which would go like m1. Okay, and then at high orders, there would be even more things. So now let me declare that M1 is the light one, and that M2 is the heavy one. So what does this look like? So this, actually, let me flip this. So remember, this came from this diagram. This would have come from the opposite diagram. So, but if I do this identification, I can pull out the powers of M2. So I always have the big one here. And this is going to be 1. Actually, let me flip them again. So this is 2. This is 1. This will be like 1, and this will be suppressed by the mass ratio. Okay. And you can already see what's going to happen. If I want to have many powers of this one, I want as many gravitons attached to this leg as possible, because remember, each graviton gave me more and more powers of the mass. Okay. So which diagrams will build the probe limit? They're the diagrams that have just one or as many insertions on the heavy guy as I can. So at leading order, I just have this. And then I add this. So this is suppressed by 1 power. This just carries 1 extra power of the big mass compared to this, because I have 1 extra insertion and 1 propagator. And then I could keep going. I could add something like this. More complicated things, higher loops. Okay. So what do all of these diagrams reproduce? So forget about the small guy for a second. This is just solving for the metric in the presence of some source. Okay, so this whole series of diagrams just becomes like a single insertion of the background metric. Okay, so this will have m squared respect to this, m cubed, but notice that this always has the same number of powers of the small mass. Okay. Yes. No, the ladder diagrams we already got rid of, right? Because we said that those exponentiated. I'll comment right now on something else, which is in the ladder diagram, there was a subleading correction, which we didn't discuss. So in this diagram, we said that the leading order went like the square of the tree. But in principle, there could be a subleading correction from expanding this propagator. So let me draw it like this, just to say that I expanded this propagator to the subleading order. And actually, that is physical and classical. I didn't have time to discuss it. So what this is this particle moving in the Newtonian potential. So this is just Gm over R, but then it recoiled. So in principle, you have other class of diagrams which look like this. So I could have the ladder at subleading order, this diagram where I expand also this propagator to subleading order, more complicated things like this. And this will resum, for instance, into 2 insertions of the background metric, where in between I have the propagation of the particle. Okay? You can count that these have the same counting in the mass. So let's do first this one. This one, it will have same power counting in the mass as this one because this was super classical, right? So this went like the tree squared, but then if I'm expanding this propagator, it's suppressed by a power of Q over M of the light guy. So I'm suppressing one power of the M of the light guy, so it just looks the same as this. Okay, and the same will be true for all of the other diagrams. Okay, so all of these set of diagrams where I have kind of a single propagator expanded to subleading order and just these kind of fans where a single graviton hits at a time, these are just reconstructing the geodesic motion of the particle in the background of this heavy particle. Okay, so we are just recomputing something that we already know, which are geodesic in Schwarzschild. Okay, so in a sense, all of these diagrams are not that interesting. I spent a long time discussing this triangle diagram, but at the end of the day, it's just kind of the leading kind of correction to the metric or the leading geodesic. Okay, yes? Yeah. Yes, that's right.
I should know. Okay, so I'll repeat the question. The full geodesic motion should be rebuilt with the 1 cross, 2 cross, 3 cross. So I should not think of the first line you compute is just the first input of a thing that I must sum.
Yes.
And that would give me the geodesic I compute in Schwarzschild.
Yes, yes. In fact, you can literally think of the geodesic equation. So how would this arise if I'm solving classical equations of motion? So the geodesic equation will look something like this. X double dot equals x dot, right? So perturbatively, I could just expand this guy, right? And I will have the full all orders in G expansion of this. That's what corresponds to these diagrams here. So these diagrams here, they are all orders in G diagrams where I just have one insertion of some object, which is classical. Actually, here I lied a little bit. It's not the metric, it's the Kirchhoff symbol, right? But then I could expand perturbatively, right? So I could invert this, right? So in momentum space, this will be like double pole, like omega squared, right? So this kind of, it's something like minus 1 over omega squared, and then x dot, x dot. So this propagator here, this 1 over omega squared, precisely corresponds to these dots. Because if I expand to the subleading order, so the leading order was 1 over p dot L, the subleading order is going to be 1 over p dot L squared. So that's precisely the frequency that would appear in the geodesic equation, right? So I just iterate this equation over and over again. So if I solve this perturbatively,
Yes, like a Picard, like a recursion or something like that.
just as a recursion, I say that x starts at some position x0, right?
Beautiful.
Plus some velocity tau, and then I have some fluctuation, right? So this, now I just solve this equation recursively. You can just check and compare to these diagrams, and you will find that the solution or the biorder precisely will match the sum over these 5 diagrams.
Beautiful. Thank you very much.
Yeah. Okay, so, but you see, we spent all of this time on the, so let me just write it here. So, kind of all diagrams with fans. What I mean by fans, I mean things that look like this. So just one graviton going all the way to the other. Multiple insertions. They're just compute the geodesic on shell action. So in a sense, we could have just skipped those. Okay. So we want to understand what is the leading correction. Okay, so that's not so interesting. We really want to understand the corrections to that because it's the back reaction. So what are the corrections? So the corrections, they're called the first 1SF, or first order in cell force. And you'll understand in a second why it's called cell force. So I'm just going to draw the generic diagram that looks like this. So here we just had iterations of these fans. But what else can happen is that I have this leg here. And then a fan means that if there's a graviton which is emitted, it will end up directly on the other side. Right? That's what these fans look like. I start with a graviton, and it will end up on the other side no matter what I do. So the correction must be that this goes back and hits the particle somewhere. Okay? So this must close. But before, it can be hit any number of times. So you can have something like this. And also, this can also talk to the other particle, in principle, any number of times. Okay, so the first correction in the mass will look like a diagram that somehow has one loop like this. Okay, let's look at the leading one. So the leading one will be at 2 loops. So it was too high, but we kind of did it the other day when we were trying to understand the emission of gravitational waves. So there was this H diagram. So let's power count. So we have the measure. Okay, let's just count powers of the mass, because that's what we actually want. So powers of the mass, we have 4 powers of 1 and 2 from the vertices. I would have m1 to the 4th, m2 to the 4th, and then there's 1 over m from each one of these propagators. Right? m1 squared, m1, m2. So this goes like m1 cubed, m2 cubed. And let's compare this with this fan, which I told you was just the geodesic motion. So this fan, now I have 3 insertions of m2. So I have m2 to the 6. I have 2 propagators here, so I have m2 squared. And I just have 1 m1 squared. So this goes like m2 to the 4th, m1 squared, which is also m2 cubed, m1 cubed, times m2 over m1. Sorry, did I do it? Yeah. So we see that it's suppressed by 1 power over the mass ratio. So what's the picture for all the diagrams that look like this? The picture is going to be, so remember, these fans hitting this leg, they were just reconstructing the geodesic motion. So this will be the same as the action for a geodesic. So now this is not a Feynman propagator. It's actually a geodesic. And then there's like a graviton that propagates in the black hole background. Because remember, these fans were just reconstructing the metric. So now I have a graviton that exits, propagates in a black hole background, and then exerts a force again on the particle. Okay? So it's just, so this first order in the mass ratio, it's just it's a classical 1-loop correction. It's like the classical self-force / self-energy. It's just computing, well, let me draw this slightly different in case this is confusing. You can think of this as a source, which is just the stress tensor of a geodesic. And this is also. Okay, so in that sense, it's a classical self-force correction. There's no actual quantum loop here. It's just kind of the gravitational force or wave emitted by the geodesic that comes back and hits the geodesic once again. Okay. So there's a whole method in classical GR called self-force where they do these calculations in position space. And it's very tricky because they do this calculation fully non-perturbatively. So they compute this propagator. Okay, this is the propagator in the Schwarzschild background. So there is no formula for this. We can only compute this numerically because we have to solve something like the wave equation with a source in the Schwarzschild background. So they compute this numerically, and they calculate this one-loop diagram in position space by regularizing some divergence here, because there's still going to be some short-distance divergence, because I could go to the limit where both geodesics are on top of each other. But when we do this using amplitudes, we're just using dim-reg, so we never see this kind of issues. Okay, so we see that this classical expansion very easily lets us identify which class of diagrams correspond to each power of the mass. So you can keep going. So you could add kind of one more graviton here. That would be the next correction in this self-force or in this mass ratio expansion. Okay. Yes.
One question. I will ask you to repeat something that you just said. So suppose I'm in a Schwarzschild black hole solution, and I can I can solve for a probe particle, the full geodesic, but I understood that you just said that this is different because this should give you the full result of the Schwarzschild plus particle plus graviton.
Yeah.
It is better than what I could have done analytically in this sense.
Yes, yes. So let me write a formula for this so that it's clear what it is. So I have a geodesic, right? And I want to compute the Green's function where the source is a geodesic, but I have to integrate over 2 copies of the geodesic, right? Because I have to evaluate the kind of the graviton source by the geodesic, and then I want to evaluate it back on the geodesic. So the action, this I, so this geodesic action at 1 SF, it will look something like this. So I have T1, T2, which are just parameters over the geodesic, right? And I will have something like x1 mu, x1 nu, g mu nu alpha beta. This depends also on x1, so this depends on T1, T2. So I evaluated the 2 endpoints. You have also M1, M2, right? So M1 times x1 dot is just the stress tensor for the geodesic. And then x2, T2, alpha, x2, beta, T2. Okay, so it's some complicated thing. So I need to have the geodesic orbits, which we can compute. But I also need to have the full Green's function for any 2 points. So this is kind of the bulk-to-bulk propagator in a Schwarzschild space-time. Okay, and so I want to compute a diagram which is kind of the integral over 2 geodesics. So it's similar to, so in ADS-CFT, there are these geodesic within diagrams, right, where you have like 2 geodesics that go like this, and then you integrate, and that gives you a conformal block, right? So this is the same, but in a Schwarzschild background. So these geodesics are geodesics of particles moving along some trajectory in the black hole background. And then this is the bulk-to-bulk propagator in the black hole background. And then I need to evaluate this integral along the geodesics. Okay? So we don't have this object analytically. But if we expand perturbatively, this just corresponds to the sum over these diagrams.
I think you just answered my question, but you said you don't have the Green's function analytical for a Schwarzschild.
Yes.
Not even Hadamard form? No, there's no.
Nothing. Yeah, actually, I don't know any black hole spacetime. Like, I'd be happy with any example, any amount of supersymmetry, anything that you like, extremal black hole, I don't care. Like, I think it would be extremely nice to find an example where one can do this computation exactly.
We just have a analytic form for any Green's function in any black hole background.
Yeah.
Since-
That's right. Yeah, 40 and above, where you actually have propagators. Yeah. Yeah.
Somewhere inside all this, you're still assuming you're in a regime where there's no gravitational wave emission, right?
Well, I'll talk about that in a second. But no. So I'll get there. So let me answer the question first. Here, some of these gravitons could go on shell, and I'll mention this next. So here I was just drawing diagrams, right? But I didn't tell you which gravitons were just mediating forces and which ones could in principle escape to infinity. And so there will, depending on the diagram, there will be a difference. It turns out that one loop, no gravitons can escape to infinity. Starting at 2 loops, they can. And this is intuitive because we were saying the other day that kind of the leading emission of gravitational wave should go like the probability of emitting 1 graviton, at least, right? So what is the probability of kind of 1 graviton? This will go like the cross-section at 5 points, right? So this will go like the absolute value of this. And this is the imaginary part of, say, for instance, diagrams that look like this, like the one I drew. So this cut is the imaginary part of this diagram. So you see that it corresponds to something at 2 loops. And the idea is that any graviton that attaches directly to one of these, we'll see in a second that it cannot be radiative. So they have to come from somewhere else, at least in the leading order in the expansion. Okay, so to summarize, in principle, one could keep going here. There's more and more corrections in the matrix that they correspond to kind of higher and higher classical quantum code loops in this sense. Okay, and this is a tricky business because this propagator has a short distance singularity, just like any 2 propagators. If you bring these points too close to each other, this is going to blow up. And so people can do these amazing calculations where they do this. And in fact, for space-based detectors, we need to go to the 2nd order. So and we don't have predictions. We have predictions for Schwarzschild, numerical. We don't have predictions for Kerr. And Lisa is going to fly in 10 years. Okay, so if any of you guys want to have some impact, you can actually try to help us compute the 2nd order in the mass ratio expansion.
It was just a quick question. This is what the has been doing, right?
Well, many people do this in various expansions. So
Okay.
the more my colleague, he computes in the post-Newtonian expansion to very high orders using this method, the self-force method. But there's other people that use this. Yeah. In fact, yeah. Anyway.
But you need like computers, right? Super powerful computers to do it.
Yes. You need powerful computers to do this. Yeah. Not the first order in self-force. This you can do on a laptop if you're good at coding. But the predictions that people need to go beyond, you can't. Okay, so just in the last few minutes, I want to describe kind of various kinds of gravitons. Okay, so what about waves? So we just discussed various diagrams, which ones are classical, which not, how they exponentiate, right? But I would like to understand what is conservative and what is dissipative. So essentially, I want to understand where the inelasticity begins, right? Which should have something to do with graviton emission or to gravitons going on shell. And once again, this method of regions comes to the rescue. Okay? And for this, it's useful to think about this limit of small velocities. Okay, so now we'll use the velocity as a counting parameter. And the statement is that there's two kinds of gravitons. There's two kinds of gravitons. They're so-called potential gravitons. So these are the ones that, for instance, build up the potential or the metric, right? So these are not on-shell gravitons. These are off-shell gravitons. So this means that their momenta, so I will split L0. So they have the energy component being much smaller than the other component. So this scales like velocity, and the other one scales like 1. Okay. So this means that they're off-shell, because if V is very small, then on-shell would mean L squared equals, L0 squared equals L squared, right? Because L squared equals 0. So if V is very small, this one is off-shell. Okay, and there's also radiation gravitons. Where both components are suppressed by the velocity. So let's just see quickly that, for instance, in this triangle diagram, or in this box diagram that we computed, there are no radiation gravitons, that there is nothing that can escape to infinity. Okay, so in the box diagram, remember that the sum over this box and this cross box went something like ddL 1 over L squared L minus Q squared delta P1 dot L delta P2 dot L. But for small velocities, P1 goes like the mass 1v, right? So this is just expand. The energy starts as m, but the kinetic energy is further suppressed in the velocity. The momentum is further suppressed in the velocity. Right? So the momentum is mv at leading order, whereas the relativistic energy just starts like m. Okay. And in particular, I can go to the rest frame of this guy, and you see that this delta function will just tell me that L0 is just 0. Okay. So in the rest frame, I have P1 equals M0. So delta P1 dot L is proportional to the delta of L0. So it tells me that this graviton is here can never go on shell. Okay, so these gravitons are just the 1 over r potential. They're not doing anything interesting. Okay, and notice that any graviton that attaches directly to one of these legs which is on shell will suffer the same fate. So all of these diagrams that we drew earlier, where we had this metric which was built by these fans, by the same argument, all of those gravitons are so-called potential gravitons, so they have nothing to do with gravitational radiation. They're just there to build up the metric.
So, sorry, but couldn't it be just simple that if the graviton escapes and you can compute the diagram, by definition, since you're computing with an escaping graviton, that is radiation or not?
Yeah, so there will be diagrams where there is radiation, not this one. This one, there is no radiation here. The kinematics don't allow it. That's the statement.
Yes, but just looking at the diagram, I mean, you're seeing that there's no graviton escaping.
Yeah, this can never go on shell. That's the statement. These legs can never go on shell in the kinematics that we're considering.
Okay.
Yeah. Okay. So this is an example, but the statement is that potential gravitons just build this the metric or potential, but they have nothing to do with radiation. Okay. Just a side comment, if you power count this diagram now with this velocity counting, you will realize that this is actually singular as v goes to 0, which is another signal that this had to exponentiate, because this actually becomes very, very large at small velocities. So you can just count, because now these guys, if they're potential, they will start as order 1, but then there's factors here which also have velocity. So if you power count, you'll see that this diagram actually goes as 1 over the velocity. I don't have time to do it, but if someone is interested, you can ask me later. Okay, so this velocity expansion also helps you identify which pieces are really not new classical corrections, because kind of new classical correction would just be smooth as v goes to 0. Okay, so which gravitons can be radiation? Okay, I already gave you an example. So first of all, just like in electromagnetism, in order to have radiation, I need to have something accelerating, right? So that's another reason why these diagrams don't contain any radiation. This is just the 1/r exchange, but this is all static sources, right? These particles haven't moved yet, right? So one option is if one of the particles recoils. So for instance, I could have the following diagram where I told you that I expand this propagator to the next order. So this one is already moving. This is moving along some geodesic. And now check that because this is not on shell, because this delta function only appears at the leading order in the expansion, this graviton here can be radiation, right? So you need acceleration to have radiation, just like in electromagnetism. Accelerated particles emit gravitational waves, but particles moving at a constant speed, they don't emit gravitational waves, okay? And another example is something like this. So if you have gravitons which are attached to other gravitons, right, this can be radiation. And this comes from nonlinearities in GR. Okay, so this is the kind of radiation that you would find in electromagnetism. So this kind of radiation from acceleration, and this one you wouldn't find in electromagnetism because there is no nonlinearities. So this is just radiation from nonlinearities. In GR. Okay. And maybe as a last comment, notice that I need to conserve energy in every vertex, energy and momentum, which means that if I'm looking at various power counting, right, I should make sure that at each vertex I conserve energy and momentum. So for instance, if I have this kind of vertex here, this is allowed because if this is a potential graviton, then its momentum L will go like 1v. And this one here is also potential, so it can go also like 1v. And this is radiation. So this can go like VV, which is much smaller. So here I have some large component of momentum that just goes through. So the energy always goes through, and then the radiation is just a small piece. But for instance, I couldn't have the following. I couldn't have radiation potential. Okay. Actually, this is a small lie, so there's some subtle reason why this can happen, which is something called the tail effect, which also comes from some nonlinearity in GR. But if you want to learn about that, I think that will be covered in the other course in December that I will give you together with Ricardo, who's here at ICTP. But see, this wouldn't be allowed because this guy here has some momentum that goes like 1v, but both of these have VV, which are too small. So there's here some large component of the energy that has to go somewhere. Okay, so there's some simple, again, power counting rules that I won't have time to explain in detail, just like we did power counting in Q. Now you can power count in the energy and free momentum components of various legs in a diagram and try to understand precisely where each radiative contribution comes from, and to read off kind of each order in this velocity expansion, which was this post-Newtonian expansion that I mentioned. Okay? So basically, everything that we know from the classical theory of GR and gravitational waves, at least in perturbation theory, so metric, geodesics, kind of back reaction from geodesics, this velocity, non-relativistic expansions for slow-moving sources, we can all identify inside of the diagrammatic expansion of scattering amplitudes. And this has become kind of one of the leading ways to perform computations of classical quantities these days. Okay, so I'm out of time, so I'll just mention that tomorrow what I'll do, so far I just focus on the amplitude, but I'll finally go back to observables and see actually what is the precise relationship between the amplitude and various observables that we would like to compute in the classical theory. Okay, thanks.